So let's get started. So today's lecture is another guest lecture, and they had Margaret Mitchell, who is a senior research scientist at Google AI. And this lecture is all about the bias that we have in data and algorithms. So let's get started. So this is the first slide in the lecture. So it was a question to the students like, what do you see in it? And they have given different answers. Something like, some people said that they see bananas, some people said that they see stickers, which we can see on the bananas, and there are different other answers that could possibly come for an image like this. So yeah, so one thing nobody said is that they see yellow bananas. So there were different answers like banana stickers, dole bananas at a store, etc. But there wasn't really an answer like we see yellow bananas, and that's because somehow when we see something like this, we like automatically associate bananas with the color yellow, especially when it comes to bananas like this. So that's something which happens, like kind of typical when it comes to bananas. So unless we have something like this, maybe then people might use color or another way of describing bananas. Like in this case, the answer could be green bananas or unripe bananas. And here we have ripe bananas, bananas with spots, or bananas good for banana bread. So as we can see here, when we have when we have the same input, there are different ways of interpreting it or saying it. So that's what makes modeling the data or using any sort of these things for some computation models very complicated. So here is another example. A man and his son are in a terrible accident and are rushed to the hospital in critical care. The doctor looks at the boy and exclaims, "I can't operate on this boy. He's my son. How could this be?" So when we read something like this, one possible thing that we could think of is that maybe it's some kind of a riddle or something that we have to think and understand. Or another thing which usually comes is that, so a man and his son both were in a terrible accident, but how come the doctor says that? But how come the doctor is in the operation theater? So these are the things that we first think of, but what people don't really think about is that there's a possibility that the doctor who is in the operation theater is a lady, and it's his son. So it's her son. So that's a possibility as well. But it's not something that that people can immediately think of, because somehow we are biased of thinking of doctors belonging to some specific gender. Not just for doctors, but normally when we are talking about things like this, things are like like specific things are like thought of in specific ways, like associating different professions to some genders and not really thinking like the other is also a possibility. So these kind of biases exist in the data and the way we treat things. So here we have a female doctor, and it's her son. So the doctor says that I can't operate on this boy, he's my son. Yeah, so the majority of test subjects overlook the possibility that the doctor is the she. So who all the candidates that were asked this question, and that included men, women, and also some feminists, and majority of these people didn't really think of the possibility that the doctor could be a female, the mother of the boy who met with an accident. So here is another interesting example. So when we take some text, and if we simply read the text, these are the kind of frequencies that that we find in the text corpus that we could find in the internet. Like words like spoke, laughed, murdered are come with higher frequencies, whereas words like exhale, blinked, hugged, breathed are seen with lower frequencies. That's because the kind of things that we naturally do, or which are kind of trivial, they are not really talked about or mentioned. I mean, when we are talking about collection of text corpus. So, but that's different when it comes to words like murdered or laughed or spoke. They are found to be in higher frequencies than words like breathed, hugged, which are kind of typical. Yeah. So the frequency with which people write about actions, outcomes, or properties is not a reflection of real world frequencies. So that this is something that we see in our data. So whenever we get started with with some task, we collect the data, and the chances of that data being representative of all the cases that it has to cover are not that good. Like whatever it is, we have like I have another blog that I'll be going through, which I wrote sometime last year. We'll be seeing some examples where the machine learning models or some computational models are being used in some very critical situations, yet the data that is being used to build such models is not really representative, which has caused some problems in the past, and it still is the case even right now. So bias is a problem. Rather than saying that it's a problem, it's something that exists, and we have to try our best to avoid any kind of side effects that we could possibly have due to bias in data. So this is how the pipeline of an ML model or some computation model would look like. So we get started with our training data, we collect all the data, and then we annotate our data, which is nothing but labeling our data, and then we train our model, and then there is some sort of filtering, ranking, and aggregation that is done, and finally we get the outputs. So this is kind of a very high level structure of the end-to-end pipeline of modeling. But there are a lot of things in each of these components, and there's also something which is common among all these, which is again bias. At each of these phases, bias could exist in different ways. Let's see here. So when it comes to training data, these are all the possible biases that we can have in the data. One is reporting bias, selection bias, overgeneralization, outgroup homogeneity bias. We have some other like prejudices. There is some group attribution error. So these are all the kind of biases that we can possibly have during the phase of training data and training data collection and annotation. So similarly, when it comes to uh, so the in at the top here we have the human biases in data, and the bias can also exist at the time of data collection and annotation. One is sampling error, and we have all these examples here. Let's say we have people who annotate the data. Like we have, whenever we are trying to automate something, uh, the first step of it is to prepare the data, and that is like always that is usually done by us humans. So let's say the person who is annotating the data, it's not like if 10 people are given the task, 10 people would do them the exact same way. And we have discussed this in the previous lectures. Like one problem that we have with NLP is that what we usually do with NLP tasks is that we take the output of our NLP model, and we compare that with the actual labels, which are actually labeled by humans, and that that in itself could involve a lot of biases, because if people are given some set of sentences, and if they're asked to classify them or say what the sentiment of those sentences is, it's very unlikely that the 10 or 100 people who are given the task will come up with the same results for every training sample. So there are these kind of problems, or there are these kind of these kind of problems exist when we are collecting and annotating data, and these are all the kind of biases that can exist at the time of data collection and annotation. So here are some of the examples. Reporting bias, which is what people share is not a reflection of real world frequencies. Like if I'm given some data and if I'm asked to annotate it, it is highly possible that what I'm doing with the data is something that is an outcome of my personal opinions. So that is also there. And then there is selection bias. So selection does not reflect a random sample. Now, whenever we are trying to collect our data for a model, for training a model, it's not always the case that we select the data in right proportion, covering all the cases or all the classes. Likewise, we have some other biases here: outgroup homogeneity bias, confirmation bias, overgeneralization, coming to conclusion based on information that is too general or not specific enough. So I think this is yeah. So overgeneralization, correlation fallacy, and automation bias. So we'll see what each of these things are in the next slides. Biases in data. So selection bias. Uh, Selection does not reflect a random sample. So this is about the mechanical Turk workers. If you haven't heard about it, Amazon has this mechanical Turk where if you have some data and if you want to annotate it, there are people who can do it for you by charging something for their time and efforts. So as we can see here, the people who are all doing these mechanical Turk, who are all acting as mechanical Turk workers, they are not evenly distributed across the globe. It's different for different regions. You can see that we have majority of them coming from the US, and then we have some in Europe and India and some other Asian parts. So this is another example of biases in data and biased data representation. Yeah. So it is possible that you have an appropriate amount of data for every group you can think of, but that some groups are represented less positively than others. Now, let's say we are trying to build an object detection model which has to detect like 100 classes of objects from the images. Now, whenever we're collecting images, we try to make sure that the number of samples that we have for each class are evenly distributed. If let's say if you're simply building a cat versus dogs classifier, and if we have 1,000 samples of cats and 10,000 samples of dogs, that wouldn't really give us good representation of data. So here's another bias that we could possibly have when it comes to annotation. Now here's an example. We have three pictures here which are put together. All of them are from the wedding ceremony, but depending on certain things that we can see in each of these images, they are being annotated differently. Like the leftmost image, we see that the kind of labels that the people have given for this is ceremony, wedding, bride, man, groom, woman, address. Then we have another very similar image where we have another couple at a ceremony, and more or less we have similar tags or labels. But then we have another couple who come from different region or different kind of culture, and they are at similar ceremony as well, but the kind of labels that the people have annotated this image with are different. We simply see person and people here. So these are the kind of biases that could exist at the time of data collection and annotation. Biases and interpretation. Yeah. So this is another kind of bias. As we can see here, I have heard the rhetoric from both sides. Time to do my own research on the real truth. So here a person thinks that, okay, I have to know more about something, and then he searches for something, and there is the first result in the Google page, which is almost whose viewpoint is almost the same as the one that he has right now. And then it's like you come to a conclusion that, okay, what I'm thinking is right. So this is one example for confirmation bias. Overgeneralization or overfitting, this is another example when you have very few classes, very few examples which are not really supportive enough for having a generalized model. So overfitting, we are familiar with this, which is a quite familiar term in ML. And here's another example, correlation fallacy, confusing correlation with causation. So here's an example. Women were allowed to vote in the early 1900s, and then we had two world wars. Clearly, giving them the vote was a bad idea. Here we are talking about two things. One is giving the right to vote for women, and then the occurrence of two world wars. There is no way that the happening of the first is something that has caused the second, but putting these two things together and saying that the one has caused the other is not really correct. So that's what correlation fallacy is about. That's another kind of bias. Then we have automation bias, in which we think when our computer says something to us, we tend to believe that it's true. So that's what it is, like propensity for humans to favor suggestions from automated decision-making systems over contradictory information without automation. So my computer predicts that I'll enjoy your coffee more, so I should have it. So this is another kind of bias. So now we here we are going back to the same figure that we have seen before. We have different components here. The training data, the modeling, and then some aggregation, and then the final output. Now, where all can we possibly have bias? Is it just in the training data phase? Let's see. So we can have human bias in training data and annotation phase. We can also have bias in other phases as well, like at the time of model training, we can have bias. We can, even at the time of aggregation, there could be bias. And finally, when we see the output, there could be bias. So bias is something which is not just about the way we collect the data, but it is about it can exist in the other in the other phases as well. As ML learns from human data, the result is a biased network effect. So when we are collecting data which is kind of biased in some way or the other, and we are using that same data without any kind of refining or filtering, and if we're using that same data for training our models, then it is kind of obvious that whatever the kind of model, whatever the model learns, is internally biased. So does it mean bias equal to bad? Not always and not necessarily. So bias in statistics and ML. So when you have a simple ML model and estimator, bias could be like the difference between the predictions and the correct values that we try to predict. The bias. So we have the bias term in the ML model. So that doesn't mean, in that case it's not like bias is bad. But what we're trying to do is we're trying to model that component into our system. And then we have cognitive biases, confirmation bias, recency bias, optimism bias, and then there's algorithmic bias as well, which is unjust, unfair, and having prejudices against some people, or different treating different races differently. There are all these kind of things which could exist in our algorithms, and they are more or less towards the bad side of bias. So here's a quote. Although neural networks might be set to write their own programs, they do so towards goals set by humans using data collected for human purposes. If the data is skewed, even by accident, the computers will amplify injustice. So this sentence kind of puts all of it together nicely. So we have ML models which are doing a lot of things right now. They are being used in medical systems. They're being used in retail. They are being used probably in almost all the industries. But whatever is being done to come up with those models, it is being done by us humans, and it is us who is collecting the data, and the goals or the the goals of each of these models are being set by us. So, which means whatever the data, whatever the biases that exist with us can get into the data and into these models as well. So when that happens, there is a chance that these models or these computers and systems can lead to some bad things. Predicting future criminal behavior. So you must have heard about things that are happening in some parts of the world right now where these kind of systems are being used for policing, like predicting crime, predicting, trying to identify criminals from their facial expressions and all this kind of stuff. So algorithms are being used to identify potential crime hotspots. So like if we have some historical data saying that, okay, we have like 3 spots in this city where more crimes are reported. So all that historical data is being collected and that is being used to model and come up with some systems that can tell us, okay, maybe at this time of the year, there is a chance of high crime happening in this area. Maybe that's where we need more security. So the ML models and deep learning models are being used in these kind of for these kind of applications. So there are arguments both for and against these kind of systems, but I don't really think so. But they keep coming. There are a few examples like faceception or something. I think we have a slide about that. We'll see what it does. So predicting sentencing. So whenever a person has committed a crime, there are some kind of systems which kind of predict uh, the risk. Okay, so if a person A has committed some crime today and is arrested, he's assigned a score. He or she is assigned a score, saying, okay, this is what the person has done, right? Like recently, and this is the person's criminal record. And now, putting all these things together, the model tries to come up with a score or a risk score saying that, okay, this is the probability of this person committing another crime in the future, and that is used to determine the sentence of for the current crime. So as an example here, there is this person called Prater who is white, and this person has been given a low risk. So the crime that this person has committed is shoplifting, and after this, the system has given Prater a low risk score. But and this person has had a previous criminal record of 2 armed robberies and 1 attempted armed robbery. And on the other hand, there's another girl, Borden, who is black, and she was given a high score for the risk factor. But the crime that she has committed is that she and her friend took a bike which was outside, but before the police arrived, they had returned it. But still, the system thought that the chances of Borden committing a crime in the future is higher than that of Prater. But but in reality, what happened was that 2 years later, Borden, the girl, has not been charged with any new crimes in spite of being given high risk. On the other hand, Prater, who was given low risk for committing a crime in the future, served 8-year prison term for some theft. So these kind of applications that try to use some historical data and come up with these kind of predictions, they can't really be perfect, and that could one of the main reasons behind that is the kind of data that they use, which is biased in a way that it's not representative of all sections of the people. Automation bias, overgeneralization, feedback loops, correlation fallacy. Okay, so here we have faceception. What faceception does is that it says that it is first to technology and first to market with proprietary computer vision and machine learning technology for profiling people and revealing their personality based only on their facial image. So what does this do? This startup, faceception, they take the images of the people And using the facial images, they try to decide, they try to recognize whether the person could be a high IQ person, or some white collar offender, a pedophile, or some terrorist. So for that, what they do is they're using the facial images and the facial expressions, and they have modeled all of this, and they try to come up with these kind of predictions. And the clients that this startup has right now are from Homeland Security and Public Safety. So here's another other example, which says that they have collected some images, uh, and what this paper says that automated inference on criminality using face images. So it's a research which uses the facial images and says whether this person could possibly be a criminal or not. And in one way, what they're trying to say is that when angle theta from nose tip to two mouth corners is on average 19.6% smaller for criminals than for non-criminals. So here, as we can see in the diagram, the lady, the image of the lady on the left, we can see that the angle theta, which is nothing but the angle between the tip of the nose and the corners of the mouth, is larger here in the left image when compared to that of the right image. So this paper says that for criminals, this angle is smaller when compared to people who are non-criminals. But to put it in another way, this is nothing but the difference between the two images is that in the first image the lady is smiling, and in the second she is not. So this is another this is some other research paper which tries to use face images for predicting criminality. So whenever these kind of things come up, it's they do get a lot of buzz on the internet. Like, people talk about it. There will be people who say that it's uh, the argument goes both ways. Like, some people state security reasons and safety reasons for in support of systems like these, and then there will be people who say that it's not fair to profile people based on their facial expressions to determine whether they're criminals or not. So here's another example, predicting homosexuality. Like, they have collected some data set, and they try to detect the sexual orientation of the people based on their face images. Here again, what it is found is that the way the model classifies or predicts things, so the differences between lesbian or gay and straight faces in selfies related to grooming, presentation, and lifestyle. So it's more about how the people's face looks in terms of the way they present and how their lifestyle is. That is differences in culture, not in facial structure. So normally when we're talking about things like this, homosexuality, it got more to do with, it could be something like, it could be more with the uh, internal things, like than the just how their face looks. But whatever this research paper does, it is just trying to use these features for determining the sexual orientation of the people. So we talked about bias, and so different kinds of biases that could possibly exist in data and algorithms. But how do we measure bias? Yeah. So normally when we try to train a model, let's say we are working on a system that does face detection. Given an image, the model or the system has to detect where the face is, like draw a rectangular bounding box around the face. Now, normally when we do it, the usual, whenever we come up with such a system, what we do is we train our model on some data, and then we finally have a test set which we simply pass and see how the results look like. But what happens is that these kind of systems might work well for certain subgroups and may not work at the same level for some other subgroup. Example, when we're trying to do face detection, rather than testing these kind of systems on a whole for some random images, it is better to test for different subgroups separately. So let's take some images of women and see how this face detection works. And then let's take images of men and see how this face detection works. So another example could be, if you're building a face detection system, you should possibly test it for both for people from different regions, like with different skin tones. So if you are training a model for face detection using data which mostly comes from the European or the Western countries, it may not work at the same level with the same efficiency for people from the Eastern countries. So these are the things that you have to be careful with. So confusion matrix. So you must be familiar with this if you have taken any ML course. This is something that you must have come across in some part of your ML journey. So we have something like true positives, true negatives, and the same goes for false positives and false negatives. We'll see examples for this. So when we are talking, when our example or the training sample or the sample that we are trying to test on, let's say you got sick and you visited a hospital and you have given a blood test, and if you have if you have something like malaria and you're tested positive, that's a true positive. And if you don't have malaria and the test says that you didn't have malaria, that's a true negative. And there are other two possibilities where you didn't have malaria, but the test still says that you had it. That's a false positive. And the same goes for false negative. So we have two different metrics for this, which is precision and recall, which uses these uh, factors like true positives, true negatives. And what we need is for a model. So here, as we can see here, the patient result. Normally, when we talk about an ML model that tries to do things like this, we simply talk about the results of the patients, but that doesn't really tell us. That doesn't really give us the entire picture. So instead of simply talking about the patient results, let's talk about the subgroups. How are the results for female patients and how are the results for male patients? And ideally, whatever the metrics that we have, the system has to report similar scores for both of these subgroups. If it has a recall score for female patient results, which is much lower or much higher than male patient results, it may not be, that could be an indication that the system is not representative enough. So these are the kind of things. The same goes for precision as well. So choose your evaluation metrics in light of acceptable trade-offs between false positives and false negatives. So uh, it's so there are two things here. One is we need the true positives and true negatives to be good, and we also want to minimize false positives and false negatives. And depending on the kind of application that you're trying to build and for the purpose and for the kind of purpose that you're trying to come up with, you should also choose between whether you want to minimize false positives or false negatives. What exactly does that mean? So here in the first example, let's say the task is to blur an image. Now here, when you have given an image of a person and it's something which shouldn't get blurred, but the system still blurs the image. So that's a false positive. Now let's compare it with what's happening on the right side. Here, we have a credit card image, and the system is supposed to blur this image so that the credit card number is not visible to everybody. But the system fails to do it, which means it's not blurred. Now, this is a false negative, whose impact is much more than the false positive that we have on the left. So it's kind of a trade-off that you have to choose. In some cases, you have to try and minimize false positives, and in some cases you have to try and minimize false negatives. And then we have spam filtering. Let's say we got an email and the system thinks that it is a spam. Now So let's say we got an email which is a spam, but the system fails to detect that as a spam, which means that's a false negative. So in the worst case, all we have is an extra email, which is not really helpful for us. But we can still go through it and say that okay, it's not something that is of any good. So let me just ignore it. We can do that. But when the opposite happens, when we get an important mail from somebody, but that is being flagged as a spam, now that's a false positive, which could have much worse impact than a false negative. So, considering all these examples, we can say that AI can unintentionally lead to unjust outcomes. So, lack of insight into sources of bias in the data and model. So, this is something which could possibly happen. Like when you're working on on some task, you're trying to build a model. It's not always that people spend a lot of time on checking what the sources of the data are and how representative the data is. So it's something that needs to be done, but it's not always done. So that lack of insight into the data could hurt the model performance and could lead to unwanted outcomes. Lack of insight into feedback loops, lack of careful disaggregated evaluation, human biases in interpreting and accepting results. These are all the kind of these all could lead to some unjust outcomes from the trained models. It is up to us to influence how AI evolves. So here, let's say, what are the short-term and long-term goals if you're in this area, if you're working in ML? So maybe right now you are working on a task, you have collected your data, and you're trying to train your model to give some good performance. And let's say you have done some research and you have come up with a new finding. Maybe then you can publish your own paper, or you can launch a product with your work that you have done so far. That's another step. And then maybe your paper is something which produces state of the art results, and maybe then your paper could get an award, and you could get a lot of fame and recognition from the research community. But the end goal of all this, if you are working in this field, should be to produce positive outcomes for humans and our environment. So, so this could be like, I mean, to think of something like this, not everybody thinks like not all the people who are working on ML and deep learning. It's not that everybody thinks that okay, I'm building something to make the world better. So it's not always the case. But this is an important slide because the current state we are in, like ML is probably being used everywhere, and we can only expect that to increase, and that's what makes this very critical. Like if you are an individual researcher, no matter what company you work for and what product that you're working on, you have to stick to your ethics so that the work that you're doing produces positive outcomes and works for the betterment, but doesn't really cause any ill effects. So that's something which is very important that we all need to be aware of. How can the work I'm interested in now be best focused to help others? So that's something that you have to keep asking yourself from time to time. It's up to us to influence how AI evolves. Here are some things we can do. Data. So understand your data. Like whenever you're working on a task, there is this urge to get done with data and get started with modeling. Like the actual fun is training the model and then seeing the results. But not all the people would like working on the data. But that's something that we all should do. Like understand the data and see how it is, so that it is properly representative of the kind of information that we need, and abandon single training set or testing set from similar distribution. So if so testing the models, so we have discussed this in the previous lectures. Like one thing that we are really behind when it comes to uh, development in ML or deep learning is that normally it's the same people who comes up with these models who also tests the models, which should never be the case. Like there should be a developer and a tester, because if I'm coming up with a model, if I'm coming up with with some work of mine, it's at the end of it, though if I'm genuinely looking into it to see what's wrong with it, I may not always find it. But when some other person does it, when there is someone else who's trying to test it, they could possibly spot some kind of problems that could be in the system. So which is so though that's the testing, the second point here talks about training and test data, but I just wanted to mention about I just wanted to mention this part about testing. Combine inputs from multiple sources. So don't just stick to one source. Try to get data from different sources. Use held out test set for hard use cases, like have a separate held out test set, and then talk to experts about additional signals. So normally when you're working on a problem, there will be a domain expert who knows everything about the domain. It's always good to reach out to them and talk to them and get get to know more about the domain of the task and the data. Understand your data skews. So there was some short video on this, like facets. I haven't really checked this, but it looks good. Maybe we can check it. Yeah, data sheets for data sets is some other. Machine learning. Yeah, so using ML techniques for bias mitigation and inclusion. Bias mitigation, removing the signal for problematic output. So having stereotypes is something which can't always be avoided. So when that happens in the data, we have to try and take care that any kind of stereotyping or any kind of racism or sexism is removed from the data. This is called as debiasing, like removing these kind of biases, stereotypes from the data, and making sure that the model receives data which is free from all these kind of stuff. So that's called bias mitigation. And then we have inclusion as well. Like going back to the face detection model, if you are trying to build something like that, you have to make sure that you are collecting data from different regions. It's not just people from the Western countries, but if that model has to work generically and across all the regions, then you have to make sure that the data also comes from everywhere, not just one part of some region. Multitask learning to increase inclusion. So this is some example of some collaboration work. The goal is to build a system that can alert the clinicians if suicide attempt is imminent. Feasibility of diagnosis when few training instances are available. So we'll see what it is. So you're trying to come up with a system that alerts the clinicians if a suicide attempt is possible. So the data for this could be like, it could come from two sources. One is internal data, like the patient health records that are provided by the patients or the patient family. So that's one source of data. And then you could also have mental health diagnosis, the historical records. And then there is social media data as well, like when people go and talk about these kind of issues on their social media, that kind of data can be collected as well. And then there is proxy data, like Twitter media data. And then when someone goes on Twitter and says things like, I have been diagnosed with X, I tried to commit suicide. So these kind of data can also be used. So this is a very simple logistic regression. What we have here at the bottom is our input features, and that is being passed through some activation function, sigmoid here, using some weights, and finally we come up with our prediction. So this is a very simple logistic regression. And then we have a deep learning model where we have the input features, and then we have some, this is a more fancier model. We have more sophisticated internal, some more sophisticated things happening internally here. And then we have multiple tasks with basic logistic regressions. We have different logistic regressions here for doing multiple tasks. So multitask learning, we have the input features, we have the weights, and we have the models tries to model different tasks, and we have different outputs here. So what's happening here is that we have different tasks like typicality, anxiety, depression, suicidal. These are the different things, and the model tries to learn for all of these tasks together. Here's the plot comparing different the performance that for different models. For the first one here is for logistic regression. Then we have single task learning, deep learning. Then we have multitask learning, deep learning, and then finally multitask learning with gender. So how exactly does it help when we're adding gender? So here, what this shows is that normally when so this is nothing but given a person's performance or something like that, the model has to predict whether the person needs to be promoted or not. Now, I don't know whether you have come across this or not. There was some time back there was this news about I think it's Amazon where the the resumes that are being filtered, it was noticed that the the resumes that are being selected for job opportunities are more from males than from females. So that's something that was talked a lot about. So here what we're doing is, if the task of the model is to predict whether to promote a person or not, we should somehow remove gender being a criteria for it. Like gender should never be a metric or a feature to decide whether to promote the person or not. So for that, what we have here is that we have a regular thing where we have the input embeddings, and one part of this model predicts whether to promote the person or not. And then we have another part of the model which tries to negate the effect of undesired attribute, which in this case is gender. So we can use this kind of architectures for avoiding any unnecessary effects of these kind of features like gender messing up the model performance or the model predictions. A classifier's output decision should be the same across sensitive characteristics given what the character decision should be, given what the correct decision should be. So whether the person is being promoted or not should never be dependent on the gender of the person. Conversation AI toxicity. So here there are some research works. So let's say these are some kind of sentences on the left, and what we have on the right is the toxicity score. So for a sentence example like I'm a proud tall person, the toxicity score is 0.18, whereas for another sentence like I'm a proud lesbian person, the toxicity score is 0.51. But there's nothing wrong in that sentence, nothing toxic about it. But somehow from the data, this model has learned to associate or relate things like lesbian, gay to being toxic, which is not really fair. So these kind of things lead to false positive bias. So here are some scores that are reported. Another example here. Yeah. So here are some plots that talk about different subgroups. Release responsibility. So normally when another thing that we talked about how the current ML and deep learning like development lacks proper testing mechanism. Another